a while since I've done this, and there's some reasons why. Um, a lot of reasons I'm auditing like as many classes as I can because if I'm gonna leave this place, I'm gonna leave with everything I can imagine I can take from this place. So, anyways, what should I start with? So I'm auditing like a bunch of classes right now. I think we should this x I, and so you're just going to data I, and then we're going to do plus data 0 equals 0. Is that fine with you guys, that notation? Yeah, I was really confused at first about the notation, but it makes perfect sense later on, so don't worry about it. No, it doesn't, but it will work. So we start with this, right? So this over here is index notation. So this will mean x1, data 1, plus x2, data 2, plus so on and so forth, plus data 0, which is over here, equals 0. So a lot of times in fluid mechanics, we stay with 3D, but here we're going to move on to multiple things. So this is going to be visualizing the D dimensions, so more than 3 dimensions. Um, Now notice that these data over here is what we're going to give a hint to. That these data one like this is going to be kind of like what we did. Let me just think of 2 dimensions, all right? If we do x2, data 2 equals 0, that looks like point slope form, right? If you remember point slope form. This is actually same as saying a line. Uh, and this goes down over here because plus theta 0 equals 0. Now, what does that mean? I mean, let's just rearrange it a little bit. It's not really point slope. It's a intercept form actually. X1 equal negative x2 data 2 divided by data 1 plus data 0. Sorry, this is not cell phone, but you remember there was another version of this you can do where you can do data 1, and I believe it's x1 minus x2, parenthesis, not x2, x110, let's just call it 110, plus data 2 x1 minus x 210 parentheses equals 0, and you get rid of that thing. Now, this can be generalized to multiple dimensions, and this is what's incredible. And you can figure this out by going to index notation. This is how a plane and other forms of that can be expressed by. And this is very interesting to me, at least. I don't know about you, but basically what you do is do this. Xi plus data 0 equals 0. Okay, well, that is true. Now, let's look at another point where it's basically data j over xj plus data 0 equals 0. Because if you think about it in a line, there's multiple points you can denote. Like you could denote it like this, you could denote it like this, there's multiple points. So this is activating another vector into it. Now, let's subtract these two. Up, subtract. And this creates a beautiful sympathy where you see these goes away equals 0. Huh. So what that shows you in reality, because this data is the same, and it's just, and we can reform this as data, um, parentheses, and then in reality, how you have to, how you write it now. So we're gonna do something called over here. We're gonna add something. We're gonna put 1 and 2, so we can change this to i's instead, and you can change this to I guess 1 and 2. That's probably the better way to do it actually. Yeah, and it's more proper index notation. So we can say this like 1 and then xj2 like this because you have two different point back points in the system, and you have this kind of system. Incredible. So what does this show me? It shows me that you can write things as a x1 plus b x2 plus c x3 plus d equals 0, or a parentheses x1 minus x1 0 by having another point plus b x2 minus x2 0, and then plus c parentheses x3 minus x3 0 equals 0, and these are equivalent expressions. That's incredible, right? By having another point, we can get rid of an d. Is what's saying. We just need two different points like this, and it feels magical, but it's not. It's just mathematics showing its power. So you need 2 points in a in a way in the same field. So if this is R, right, 2 points in R2. If it's R3, then it's going to be a 3D like this. And then here's the thing. You can get to R4. So R2 is going to be a line like this, right? And then R2 is going to be like a plane like this, like and then you need 2 points over here and then 2 points over here. I guess that's kind of R1. I mean, there's multiple R2s I can define it. So it's depending on your definition of looking like. We're talking about multiple planes then. Yeah, so you can't visualize greater than that. But mathematically with tensor notation, you can. And that's the power of index notation, in my opinion. It shows you beyond the scales of a three-dimensional world. You can go to 10, 16, 27, 30, 30 vectors. It can still give you something that works, even though there's no visuals. So index notation has incredible power, but you have to follow the rules.